Yeah, so why do we do parallel operation of transformer? Any basic idea behind it?
So to supply power to more load.
Yes, if in case load has been increased, then the rated of then the rating of your transformer, then we have two options. One is to replace the transformer with higher rating. So that is not desirable because you will have a spare transformer. If you are replacing, you are creating a waste of a spare transformer. And and in many cases, if you want to uh, if your transformer got damaged or any problem occurred in that transformer, then one of the two transformers or one of the many transformers can supply to the partial fraction of the load. So in those scenario, it is advantageous to connect multiple transformers in parallel rather than just connecting one very large transformer to supply that load. And another thing is that uh, it is economic. It is economic to install other transformer in parallel rather than replacing it with a larger unit. Also, if uh, if reliability is our concern, because in transmission lines or in our operation of the transformer, if reliability is the major thing that everybody is concerned, because if transformer got tripped, then you don't want to stop all of your work. In that case, at least partial fraction of the load should be supplied from somewhere, and in those cases, multiple transformer helps. Okay, so these were the basic idea behind it, and there are certain conditions to satisfy the successful operation of transformer connected in parallel. Okay. Uh, One thing is that they must be connected properly as far as their polarities are concerned, so that net voltage around the local loop is zero. You know that when two transformers are operating in parallel, so they will have certain leakage impedances. So we don't want to flow any circulating current in the circuit because uh, our leakage impedances, the quantity of leakage impedances are fairly small, and in such case, you will end up with very high circulating current. So we don't want that case to be happen. And we will solve one problem based on that, where our voltage is not equal. Voltages of two transformers are not equal, and in such cases, you have to supply to a load. And in those cases, what will happen and how much load will be catered from which transformer, that we have to see. Okay, so I guess you are able to read the problem which is on your screen. Okay, here in this problem, we have two parts. When we have the same voltage, okay, we have the two transformers which have same voltages, and in B part we have different open circuit secondary voltages, in which I guess you might have already observed that there will be certain circulating current that will be flowing in part B. So we will see how to handle such kind of problems. Okay, so do you guys have any issue in formula or theory? Should I brush up the formula, or should I just straight away dive into this problem solving? What do you want?
Sir, which formula?
When transformer operates in parallel, there are two cases with equal voltage ratios and unequal voltage ratios. So you know this formula, right? S1 is equal to SL. The rating of S1 and SL will be determined by impedance. Do you know this formula?
No, sir.
Oh, you don't know. So, okay, let me just brush it up, okay, for you guys. So basically, we have two transformers which are connected in parallel. So how will they look like? This is a one transformer, okay, and there will be other transformer. Let us call it E2. EMF is induced in that transformer with certain impedances like JX2, R2, R1, and JX1. Okay, both are connected in this fashion, and we have to cater a load which is variable. Okay, now how to how to provide this load and in what ratio these both transformers should operate such that one any one of them should not get overloaded. Okay, these are primary concern such that one case arise where load becomes directly proportional to the kVA rating of the transformer. Okay, so there will be some certain current here. Let me I1. Okay, here
Sir,
I2.
can you show the question?
Okay, this is the question here.
Sir, your sound is not audible clearly.
Okay, is it happening to everyone or is it happening just to Deepak or Adil who is speaking? Is my voice not audible properly? Can everyone confirm?
Sir, you are audible and slide is visible.
Okay, great, thanks. So, Adil, what do? You just log out from the meeting and rejoin the meeting such that your network might be restored if any glitch is there. Okay, so I was discussing that this is the scenario where I1 will be current that is originated from the transformer 1 and I2 is the current that is originated from the transformer 2, and there will be some load current, right? So we have a KCL expression I1 plus I2 is equal to IL. Okay, now what will be the ratio of I1 and I2 with respect to load current? Okay, there will be certain voltage here, V, and the desirable thing is that V is equal, okay, or E1 and E2 should be equal. This is the desirable condition. E1 should be equal to E2. Okay, and V, as you know, there will be certain drop from E1 and E2, and V will be less than E1 and E2. Okay, now we have to provide a proper ratio to cater this load. So we have to apply I1 with respect to IL. I1 is equal to IL into current division rule, okay, Z2 divided by Z1 plus Z2. Okay, similarly, I2 is equal to IL into Z1 plus Z1 plus Z2. Okay, and I1 plus I2 is equal to IL, we already know. Now we know the KVA rating provided by the first transformer will be V1,
Sir,
V, yeah.
sir, I did not get this point. IL into Z2, I Z1 plus Z2.
See, you know current division rule, right?
Yes, sir.
Yeah, so you apply current division rule from I1, I2, and this is a parallel branch. Okay, so this I1, sorry, yeah, this I1 relationship with IL, how to calculate according to the current division rule?
Okay, sir. Here IL is a total current.
Yes, yes.
IL Z2 S, sir. I got it.
Got it? Okay, great. So now S1, the kVA rating provided from the transformer 1 will be V into I1 conjugate. Similarly, S2 will be V into I2 conjugate. Okay. So now if you multiply here V on the both side, so it will become this expression will become S1 is equal to SL, okay, into Z2 divided by Z1 plus Z2. Okay, we are not worrying or bothering about conjugate because at the end of the day we can take care of it. But we are just simplifying the things here. How the share of each transformer will go to the load. Okay, similarly, S2 will be SL into Z1 divided by Z1 plus Z2. Okay, agreed. And hence S1 plus S2 will be equal to SL. Okay, now what is the ratio of S1 by S2? Can you tell me what is the ratio of S1 by S2?
Z2 by Z1.
Great, Z2 by Z1. So basically, a kVA rating of each transformer is inversely proportional to its impedance, its leakage impedance. Okay, so that is very important expression that will become handy in solving problems. Okay, now in this expression, S1 and S2 expression, many a times we will be given with per unit quantities, but we have here two different impedances. So whatever per unit quantity you will consider, for that case a base will be required, and that base should be common for both the impedances. So if you are considering S1 is equal to SL and you are considering Z2 per unit divided by Z1 per unit plus Z2 per unit. So base impedance for both the transformer, actually both the impedances should be derived from the same base. Otherwise you will get different values. That will be much clarified in the problem. Okay, so base impedance should be same for both impedances. Okay, so this was the basic. Any doubt in this part? The major thing you need to recall or remember always that ratio of kVA is inversely proportional to its leakage impedance. Okay, it is very important relationship. Okay, so if it is fine, then what we can do is we can further manipulate this equation. Okay, so we are going to write Z2 by Z1 is equal to S1 by S2. We can write it as VL into I1 divided by VL into I2. Okay, now we can write it further. Z2, 2 sorry, Z2 I2 by VL is equal to Z1 I1 by VL. So what you can observe from this expression where we are heading to the one very important expression, that when a transformer is operating directly proportional to its rating, in that case, per unit impedance of both the transformers will be equal. But there is a catch, it will be in their own base. Okay, so both will be equal as soon as you see in the problem it is mentioned that load sharing is directly proportional to its kVA rating. You can immediately apply this expression. But you have to take care of one very important thing, that both impedances are in their own base. Okay, what do I mean by in their own base? That will be pretty much clarified in the problem. Okay. Now, I would like to extend this theory a bit further. What happens when any transformer is overloaded? Okay, so if their loadings has to be in ratio of their respective kVA ratings, it means their per unit impedances should be equal. But what happens if they are not equal? What happens if transformer 1 has lesser kVA rating compared to transformer 2? That is the actual scenario in this problem, that you can see one transformer is 600 kVA, other transformer is 300 kVA. So the 300 kVA transformer will reach the limit very quickly compared to the first transformer. In such cases, how to identify the maximum loading that should be catered from both the transformers? Okay, so that is very important thing. However, in the problem, it is already said that we have to cater 800 kVA. But whether these transformers are able to cater that 800 kVA without getting overloaded, or it is getting overloaded. So most probably, from my guess is, second transformer will get overloaded, because if you see that secondary transformer has very less kVA rating compared, almost half, not almost, exactly half of the first transformer. So if you add simply 600 plus 300 kVA, so in that case it will become 900, right? And our load is 800. So when they will reach equally 300 and 300, then it can cater 600. So we will see the formula, what will happen in such cases. What will be the maximum load kVA rating that could be catered from both the transformers of such rating without getting overloaded. Okay. So do not get worried. We will solve this and you will get acquainted with these concepts. So yeah, I was saying that both should be in their own basis, but what will happen if one transformer is overloaded? So let us infer from this expression that S1Z1 is equal to S2Z2. This is the relationship. But let us assume first transformer is overloaded already. So it means S1Z1 will be less than S2Z2. Okay. If transformer 1 will reach or will overloaded, but first. Okay. So in such case, how to identify the maximum capacity of the load? So we can calculate S1 rated. The contribution of transformer 1 would be SL max. Let us assume some maximum amount of load that could be catered from the transformer 1. Okay, so into Z2 divided by Z1 plus Z2. Okay, so from this expression, you can get the expression of maximum loading. SL max is equal to S1 rated into Z1 plus Z2 divided by Z2. So this expression will determine how much the limit of the load that could be catered from the lower rating of transformer. Is it clear till this point?
Sir, what does that final equation signify?
This final equation signifies that the maximum load can be catered by the lower rated transformer without getting its overloading. Okay, so we have to cater the load without overloading any transformer. So here we assume that our first transformer has the lower kVA rating, so it is guaranteed that first transformer will be overloaded. Okay, when S1 Z1 is less than S2 Z2. In such case, how much the maximum load that can be catered by the transformers without getting its overloading. So this expression will lead you to exact quantity of maximum value of load that can be catered from both the transformers without getting transformer 1 overloaded. Did you get it? Adil, did you get the point?
Yes, sir.
Great. So any doubt till this point? Okay, if not, then I would like to complete this. Okay, just for the sake of completion, I would like to write similar scenario if S1 Z1 is higher than S2 Z2. What does it signify? It signifies that transformer 2 will be overloaded. In such case, what should be the maximum amount of load that should be there? Okay, so SL max should be equal to S2 rated into Z1 plus Z2 divided by Z1. Okay. Now, and in both cases, you will have something SL max. It should be less than S1 rated plus S2 rated. Okay, so in our question, S1 rated plus S2 rated is higher than SL max. Okay, so it means there is going to be one transformer that will be overloaded. Okay, if this condition satisfies, then there will be some one transformer that will be overloaded. So overloading condition will occur. Okay, then this was the scenario when we had equal voltages. Okay, we have another scenario when voltages will be not equal. In that scenario, we will discuss, that is the part of this problem, which is in part 2. But first, we will try to solve the part A with these much concepts. Okay. So now, let us solve this problem. Okay. So we have Z1, we have Z2. I would like to write it down. Z1 is equal to 0.012 plus J 0.06 per unit with 600 kVA and 440 volts. Okay, I am writing both the rating of the transformers. Why? Because to consider when we are going to apply this ratio of loading, in that case we have to consider equal amount of base impedance. Z2 will be 0.014 plus J 0.045 per unit, okay, with 300 kVA and 440 volt. We have load which is having kVA rating of 800 kVA at 0.8 power factor lagging. Now we have to find out how they will share the load. Okay, how they will share the load. Now to find out how they will share the load, we have to apply S1. We know the formula S1 is equal to SL into Z2 divided by Z1 plus Z2. Okay, so but we have given the impedance values in per unit, and we want to simplify this problem with per units only, but we have to bring at the same base level of the impedance. So I would like to convert Z2 with the base of Z1, okay, because it has the higher rating 600 kVA. So Z2 per unit impedance in terms of base value of Z1, if you will convert, we have certain formula that impedance value Z per unit new is equal to Z per unit old into kVA new divided by kVA old. That is very famous formula, okay, into kV square old by kVA square new. Any doubt in this expression?
Sir, why we are doing this?
We are converting impedance on the same base level, okay, such that we do not mess up while computing load sharing of each transformers. So we have to bring at the same base level, because you know, if you plug in this Z1 at, sorry, if you plug in the value of Z2 with the base value of 600 kVA and 440 volt, and you will plug in the value of Z1 with 300 kVA and 440 volt, you will get bizarre result. Okay, so we don't want to happen that. Got it?
Sir, from this formula, both the per unit impedance have same base value of current and voltage.
Yes, if I will convert this Z2 in terms of 600 kVA and 440 volt, then both the impedances will have same base unit. Their per unit values will be referred to the same base value, so that we will get proper answer. Otherwise, the other way is to convert both of impedances in actual values, and then you just plug in the actual values. Okay, but since per unit values or per unit approach is considered as more convenient, we should go with per unit values, right? Is it fine, Deepak?
Yes, sir.
Okay, so I hope there is no problem with this expression. Okay, so now I would like to compute Z2 per unit new, right? So its old value is 0.014 plus say 0.045. kVA new is 600, okay, and kVA old was 300, and kV old and kV new both are same, so we don't have to worry about it. So basically Z2 per unit new value will be 0.028 twice of whatever the earlier values, 0.09. Okay, I hope it is fine, right? Okay, we have computed Z2, Z1. Now, we will find out the share of transformer 1, S1, in terms of SL. Now we have to consider the magnitude as well as angle, Z2 per unit divided by Z1 per unit plus Z2 per unit. Now SL is 800 kVA. Okay, you can see that 800 kVA with 0.8 power factor lagging. Okay, so if you don't want to go into trouble of conjugate things, you can write SL in the terms of, you know, your current. So basically, I would like it as 800 angle minus 36.86. Okay, I am simplifying here. The standard thing is in many books you will find that if it is lagging power factor, the apparent power is written with SL angle positive. Okay, so this angle would have been positive, but if you write it in terms of positive, then you will have to consider in terms of conjugate. You have to do conjugate of this whole thing. That would become messy. Okay, so this is simplified approach where you can avoid the conjugation thing, and we will see at the end how much power factor and this magnitude will come out to be. Okay, so this is SL. Now Z2 per unit. Z2 per unit we have computed 0.028 plus J 0.09 divided by Z1 0.014. Oh, sorry. Z1 is 0.012 plus J 0.06. J 0.006. Oh, sorry. Plus Z2 0.028 plus J 0.09. Now please calculate it for me. Okay, so that we can write it, this value. Similarly, S2 will be 800 angle minus 36.86. Now this time Z1 per unit will be on the numerator. Okay, so 0.012 plus J 0.06 divided by 0.012 plus J 0.06 plus 0.028 plus J 0.09. So both values I want from you guys. So did you guys get this much? 485 angle minus 39 degree, and the second is 315 angle minus 33 degree. Did you guys the same values?
Sir, we are still calculating.
Okay, please take your time. So I would convert in the meanwhile in real and imaginary. 377 minus J 305.2, 264 minus J 171.6.
Sir, I have an answer, but it is not exactly the same, but very close to it.
Okay, so could you please tell me that?
Sir, in polar form, it is 486.47
Mhm.
with angle of minus 39.24. And
Okay, means it is. Yeah. So it means it is correct, right? Because it is very close. And secondary transformer also getting the same value.
no, sir, I have not calculated that. I was busy with the first one.
Oh, okay, no problem. So I think it is correct. If first is correct, then second should be correct. Okay. So, okay. Now you have the values of load sharing by both the transformers. Now, have you observed anything in these values? What can you see? Okay, let me simplify it for you. This transformer had the kVA rating of 600 kVA. This transformer had the kVA rating of 300 kVA. Now, are you able to see something?
Sir, second one is overloaded.
That's it. Second transformer is overloaded, and load is not shared in proportional to their kVA ratings. Okay, because 600 kVA is supplying 485 kVA. Okay, it should have supplied at least close to its rating, and the other transformer rating is 300 kVA, and it is supplying 315 kVA, which means it is overloaded. And why it is happening? Both are not supplying proportional to their kVA ratings, because the basic thing is uh, we have two transformers, and it is not satisfying the condition of parallel operation of the transformers. Necessary condition it is satisfying, but desirable condition it is not satisfying. Okay, so if it means S1 Z1 is not equal to S2 Z2. Okay, after the session you can calculate both the values and you try to equate, and you will see that S1 Z1 is higher than S2 Z2. Okay, so this is kind of your leisure work, leisure time work you can perform now. So and this transformer is overloaded with 5%. How I am saying it is overloaded with 5%? Because 300 kVA was its rating and 315, so 15 kVA out of 300, which will be 5%. So it is overloaded with 5%, and its per unit impedance is also very high compared to first one. If you see, per unit impedance is high compared to this one. So that has to happen. If such case will be there, S1Z1 is sorry higher than S2Z2 because this 300 kVA is second transformer. So it has to happen. Now, the important thing is how much load should have been there such that second transformer, it is wrong to say secondary transformer, second transformer would not have get overloaded. Okay, so for this purpose I have derived this expression, right? If you recall, I have derived this expression, right? And here second transformer is getting overloaded, so we have to consider this case. Okay, when S1Z1 is greater than S2Z2, I told you. Now we have to identify SL max, the maximum load that can be catered without overloading of any transformers. So what will be the value here? SL max is equal to S2 rated into Z2 plus Z1 divided by Z1. Am I right? This is the expression, right? SL max S2 rated Z1 plus Z2 divided by Z1. Now this expression will give us, this is the 300 kVA, okay, 300 kVA into Z2 plus Z1 was how much? 0.04
plus J 0.15.
J 0.15, great, thanks, divided by 0.012 plus J 0.06. Okay, so how much this will come? That we have to see. And other thing I forgot to mention here, you are getting in output 315 angle minus 33 degree. Here minus is coming and we have taken load as minus with lagging. It means this is lagging kVA that is being supplied from the transformer 2 as well as transformer 1. Okay, so we avoided the complexity of conjugation. Okay, because in that case many times we end up doing some silly mistakes. To avoid that, you just think in terms of conventional. When lagging it means minus, when leading it is plus. Okay, you just go ahead with it, and at the end you will get the value, and in outcome you will, if you get minus it means lagging, if you get plus it means leading. Is there any doubt about this? Because it is very important thing, and many times even I have done mistake in this. So it is very important to grasp this, okay? Because it simplifies the calculation, and this calculation is a bit tricky. I always find it a bit tricky. Okay, so I hope it is fine. If any doubt, please let me know. And here, how much SL max is coming, also please let me know. Okay, so if I will simplify it, 300, if I have to consider only magnitude, so it will be 0.155 divided by 0.061. So it will come out to be 762.3 kV. If you are done with calculation, please let me know you are also getting the same.
Yes, sir. 761.114 at an angle minus 3.6.
761.114 at an angle minus
3.62.
3.62. Thanks a lot. So it is close to that value. Okay, so what does this value imply? 762.3 kVA, what does this value imply?
Sir, it is the value in which
Sir, it
both
is
the
a maximum
transformers can
loading.
safely.
Please go one by one. First, Neeraj, you complete it. Then Deepak, you can complete.
Sir, we can apply a load up maximum up to 761 kV so that none of the transformers gets overloaded. If we exceed this value, then one transformer will get overloaded.
Yeah, you are perfectly correct. But specifically in this case here, transformer 2 will be overloaded. Okay. Because we have considered 300 kVA rating because S2Z2 was less than S1Z1. Hence, transformer 2 should not get overloaded. It is certain that transformer 2 will be overloaded first. Okay. So we have to avoid that case. You are perfectly correct. One of the transformers should not get overloaded. But we deduced earlier that transformer 2 is going to be overloaded. So we avoided with this much of maximum kVA rating. Okay, if this much amount of kVA rating is present on the load, then none of the transformer will be overloaded. Yeah, Deepak, you want to add on something?
No, sir, I want to ask something.
Yeah, please go ahead.
Sir, here what is showing this angle minus 3.62?
Minus 3.62 is the lagging. It is the power, it is the lagging load that could be catered if you increase or decrease this angle. Okay, so let us suppose that you are increasing this angle. It means you are going to the positive side. It means you are having, let us suppose from minus 3.6 to 0 degree. It means you do not have any requirement of lagging power from the source side or from the any transformer. Okay, so whatever you will have, that will only have only real power. But if you reduce it, you will have certain lagging load and you will increase your reactive power demand. Let us suppose from minus 3.62 to you went up to 15 degree. Okay, so 761.14 angle minus 15. So if you break into cos and sine, you are reducing your P and you are increasing your Q but lagging. Okay, so this lagging load has to come from the source. If it had been leading, it means your load is supplying back reactive power to the source. Did you get it?
Yes, sir.
Any further doubt?
Sir.
Okay, great then. So we are done with part A. Okay. So even though the sum of the ratings of the two transformers was 900 kVA, we end up with overloading one of the transformers. Okay, so this has happened. Why? Could you please let me know why this has happened? In fact, we had sum of both the transformer ratings was 600 kVA plus 300 kVA. That is 900 kVA. And we have load only 800 kVA. In spite of the fact we have higher kVA rating from the source side, we end up overloading one of the transformers. Why did it happen?
So the equivalent impedance were not according to the required ratio.
Yes, yes. So your kVA rating ratio is not inversely proportional to its impedance. Okay, this reason, where did I mention it? Load is not.
Right side, furthermore, right side.
Yeah, this one. This ratio is not satisfied. That's why it happened. Okay. I
Sir,
hope.
if this
Yeah, go ahead.
sir, if this condition will satisfy, then just we have to add then add them KVA rating, and we can say the maximum load we can connect this much amount.
If this ratio will be satisfied, in such case, none of your transformer will get overloaded. Okay, so that's why I broke into two cases where S1Z1 is less than S2Z2 or S1Z1 is greater than S2Z2. Only two things can happen, right? So it means if anyone is less than other, it means you are not providing appropriately according to its ratio, right? So it means your one of the transformer is going to be overloaded. Okay. I am emphasizing very much on this part because it is very important in all the exams. This concept must be checked, okay, and it get checked frequently. So better you fix it in your mind that how to calculate and how to take care of per unit things, okay, how when to consider per unit and how on which base values, okay, where that you should take care. So please solve 2 3 problems based on parallel operation of transformers. You will be well acquainted with it. Any last doubt from part A? When both the voltages were equal, now we will see what will happen when both voltages will not be equal.
Sir, in this case, if this condition will satisfy, so we can connect 900 kVA load.
Yeah, you can connect. If S1Z1 would have been equal to S2Z2, then you could have easily connected 900 kVA. Oh, sorry, 800 kVA.
No, sir, 900.
The load
We
is
want.
800. Load is 800
Uh,
kVA, right?
sir, as suppose we want increase the load.
If you want to increase, then you have to check at that load what will happen, right?
Okay.
Because kVA rating is not a scalar quantity, it is a phasor quantity. So you have to check at what power factor it is operating. Both things should be satisfied because power rating, power factor here signifies that how much real power and reactive power demand is occurring at the load side. According to that, your transformer will supply.
Yes, sir.
Yeah. Okay then. So now in part B, we have open circuit secondary voltages, okay, with 445 volt and 455 volt. Now, if both voltages are not equal, it means some circulating current will flow in the circuit. Okay. So let me first derive the case when unequal voltage ratios will be there. In the case of unequal voltages ratio, from this equivalent circuit, okay, let me copy it. Yeah. So now we are considering when E1 is not equal to E2, and we are given with E1 as 445 or 455. It is 445. E1 is given as 445, and E2 is given with 455. Now there will be some circulating current, okay, at load or no load. Why? Because there is difference between E1 and E2, and that circulating current will be high because these are the leakage impedances. So, and both of them, the small quantity will be in denominator. Let me compute this circulating current. It will be E1 minus E2 divided by Z1 plus Z2. So these are very small, okay. These are also not very high. So basically circulating current will increase, and that will lead to copper losses, okay, and reduction in contribution of KVA rating to the load. So if I want to compute E1 in terms of load current, okay, so E1 is equal to, apply the KVL in this loop. Let me apply the KVL in this loop. It will be E1 plus E1 is equal to I1 Z1 plus IL ZL. And IL is nothing but I1 plus I2. Okay, so this is the expression of E1. Now, if you see E2, similarly, it will be I2 Z2 plus IL ZL, and you will end up with I2 Z2 plus I1 plus I2 ZL. Okay, and circulating current we have already computed. This one, circulating current, and this circulating current will be equal to when there is no load, okay, at no load, circulating current will be equal to I1, okay, and it will be equal to minus of I2, and it is nothing but E1 minus E2 divided by Z1 plus Z2. Any doubt till now?
Sir, this expression came from where?
This expression came from this equivalent circuit, this circuit.
This I1 equal to minus I2.
At no load, if there is no load, let us assume this load is disconnected, then what will happen? I1 is equal to minus I2. You can see this is I2, this is I1. At this node, I1 is equal to minus I2.
Yes,
and
sir.
This is equal to E1 minus E2 divided by Z1 plus Z2. Okay.
Yes, sir.
Okay, great. And when this circuit is short circuited, okay, this is the case of no load. When short circuit will happen, then what will happen? If a short circuit is happened here, in such case, I1 is equal to E1 by Z1 and I2 is equal to E2 by Z2, because both current will go in this fashion. So this load section will be disconnected and sorted. So this will be the expression. Now, when we are loading it, when we have this load or any certain load, in such cases, we will have some I1 and I2. So I am deriving this expression because part B is related to this thing. When circulating current comes in the picture, then things become a bit complex. Okay, it's just KVL equation, but you need to take care of this, right? So in such case, E1 and E2 and I1 and I2 becomes these things I1 Z1 and I2 Z2. Okay, so you have to take care of this expression only. And circulating current comes because in circulating current many times you might not be given with load current and you have to go ahead with ZL only. So let us focus on the problem now. I think we are well aware with the concept and we can solve this problem. Okay, so yes. Okay, I will just drag it. Okay, so this problem was when the open circuit voltages was 445 and 455 volt and terminal voltage of 440 volt. Then I have to compute how the load will be shared. Okay, so that was the problem. I hope you remembered it because we do not have enough space here. Okay, so in such case, first we have to go ahead with actual values in such cases. Actual values, if I want to compute Z1 actual, and Z2 actual, then we will be able to compute the circulating current, right? E1 minus E2 divided by Z1 plus Z2. So Z1 actual will be equal to 0.012 plus J 0.06 divided by Z base of 1. Similarly, Z2 actual will be 0.028 plus J 0.09 divided or multiplied.
Multiplied, sir.
Multiplied, yes. Into Z base 2. Okay, so what is Z base 1? Z base 1 will be KV1 square divided by MVA1. So here we have the voltage of 440 square. Okay, so we are having the 440 volt of voltage at the terminal and kVA rating is 600 kVA. Okay, so we are calculating at the same base value. Okay, do we need to compute at its own base or same base? Because if it will be their own basis, then I don't find anything here. Let me confirm it from the expression. So this 0.014 per unit of resistance with 0.045 per unit of reactance. Okay, and we have to compute at 600 kVA, right? So why this is happening? Because we had to convert at the same value of base in part A, right? So here also we want to convert the actual value with the same base, with the higher base, such that we have to avoid this number. Now it will come out to be 440 square divided by 600 kVA. 440 square divided by 600. So it is 0.3226. Okay, so this base will be multiplied to the both side, and now Z1 actual will become 0.0039 plus J 0.0194. Similarly, Z2 actual is equal to 0.009 plus J 0.029 ohm. Okay, these are the actual values. Otherwise, we would end up calculating the wrong values if we use different base values. Now the load impedance has some, we have to compute load impedance or load current, because we know I1 plus I2 is equal to IL. So this load impedance ZL, how to compute this ZL? Because we have load kVA, we have load voltage. So voltage square by kVA. Okay, 440 square divided by 800 kVA, and this kVA is lagging minus 36.86. So how much this impedance will come out to be?
So 242.
242, any angle?
Angles are same, positive 36.86.
Yeah, 36.86. Isn't it very high? Is it 0.242 or 242? You might have missed this 10 to the power 3. So, sorry. Am I right? You left this 10 to the power minus 3, 10 to the
Yes,
power
sir, I
3.
have left the power.
So this is your ZL. Now we have Z1, Z2, ZL. We can calculate the currents I1 and I2, right? Because we have this expression. So according to this expression, if I have to compute I1, we have to do what will be I1? I1 is equal to E1 minus I2 ZL divided by Z1 plus ZL. Okay, so let me write it. I1 is equal to E1 minus, am I right? E1 minus I2 ZL, E1 minus I2 ZL divided by Z1 plus ZL. Okay, so I hope it is fine. And from this expression, I can calculate I1, which for E1 was 445, angle 0, minus I2 we haven't calculated, right? So I2, how to substitute I2? That is another thing. So we have second expression. We have second expression I2 in terms of E2, right? That's why these both equations are very important. Now I2 you can write similarly E2 minus I1 ZL divided by Z1 ZL plus Z2, right? Yeah, ZL plus Z1. Here I know I2 is equal to E2 minus I1 ZL divided by Z2 plus ZL. Okay, you have to substitute this I2 in this here. You will get a value and that will lead to I1. And again, if you substitute that value in I2, you will get I2. Okay, so for that, if you calculate, this is a bit lengthy calculation, but anyway, we have to go ahead with it. So for that purpose, I did not derive it here, but I will simplify it here. Okay, what you will get essentially I1 in terms of E1 and E2. I1 is equal to E2 Z1 minus E1 minus E2 ZL. Okay, I'm simplifying the expression so that you just plug in the value and you will get the expression at one hand. Z1 Z2 plus ZL, Z1 plus Z2. Okay, so this is the expression of current that will be originated from the transformer 1 to cater the load, and similarly you will have I2 which will be E1 into Z2 minus E1 minus E2 into ZL divided by Z1 Z2 plus ZL Z1 plus Z2. Okay, isn't it simplified? Now you can easily compute both the I1 and I2. However, this expression is very long, but anyway, it is much better than substituting two equations in the exam, right? So if you compute now, I1 is equal to E2 was 455 angle 0, and Z1 we have Z1 in terms of angle we did not compute it, so let me write in terms of polar form. Z1 is zero point 0198 angle 79 degree, and Z2 actual is 0.0304 angle 73 degree, and ZL we have computed in terms of polar. So I will just plug in the values. Okay, so E2 into Z1 is 0.0198 angle 79. Okay, minus 445 angle 0 minus 455 angle 0 into ZL. ZL is 0.242 angle 36.86 right? Any doubt till this point? Divided by Z1 into Z2, that is 0.0198 angle 79 degree into 0.0304 angle 73 degree plus ZL into Z1 plus Z2. So ZL will be 0.242 angle 36.86 into Z1 plus Z2, 0.0198 angle 79 plus 0.0304 angle 73. I know this is a long calculation, but this is the way we have to compute, right? So after calculating these values, you will get I1. Okay, please calculate it for me. In the meanwhile, I will write the expression of I2, and then when we will add I1 plus I2, that will be IL. Okay. So let me write the expression of I2 here. Similarly, that I2 will be 450. I2 is equal to E2 into Z2. Okay, so E2 into Z1, I have already written here. I will just try to plug in these values. I2 is equal to, sorry, E2 into Z1. Here it would have been E1 into Z2. Okay, so I will leave it for you to compute I2 value and I1 value. Okay, and what you will get at the end, you just have to multiply with 440 volt, 440 volt into I1, that you will get S1, and 440 volt into I2, that you will get S2. Okay, so if you get both the values, then what you have to do, you have to compute S1 plus S2 real power and reactive power, and then you will see at the end what is the value of whether one of your transformers are getting overloaded or not, or if overloaded, by how much percentage. If not, then it is fine, right? So that you need to consider. Is any doubt in this problem apart from this big expressions? So when circulating current comes in the picture, then thing becomes bit complex. Okay, that's another bad thing about, from calculation perspective. And one thing is that it increases the copper losses, as you know. So it is desirable that there is no circulating current in the parallel operation of the transformer. Okay. So if you can see that circulating current here, circulating current, I think we have calculated. Circulating current will be equal to
I1 plus I2.
no, circulating current will be equal to E1 minus E2 divided by Z1 plus Z2 when load is not there. I1 plus I2 is load current. Okay, so 455 minus 445
Sir,
divided by,
circulating current is at no load condition.
yeah, at no load condition. Why we are saying? Because at loaded condition, if you see this circuit at loaded condition, I1 plus I2 is some of its part is getting here circulated and majority of its part is going into the load. So I1 plus I2, when load is there, you cannot say that it is circulating current. But when load is disconnected, then I1 is equal to circulating current or minus I2 is equal to circulating current.
And sir, why we don't want this circulating current?
Because if circulating current is flowing in this circuit and there are two resistances, right, R1 and R2, so both will lead to some losses, right? And because of that circulating current, uh, your calculation is also become much complex than earlier case. Right? So
Yes.
from calculation perspective, it is going to be difficult, and from practical reason, your losses are going to increase.
Yes, sir.
Yeah. So you see here, circulating current is E1 minus E2 divided by Z1 plus Z2, and E1 minus E2 is 10, and Z1 plus Z2, you have to take mod, that will come out to be 0.05. Okay, so it is 200 ampere. You see, very less leakage impedances, and very less difference in the no load voltages. Also induced EMF, the difference is very less, 10 volt, and leakage impedance is very small, and because of it, your circulating current is very high, 200 ampere. And if you see losses, 200 square into R1 plus R2. Okay, so whatever R1 plus R2 we have calculated, 0.039 plus 0.09 means 0.048. 0.048. If you calculate, this will give you the copper loss, 200 square into 0.048, that is 1.92 kilowatt. Okay, so this much copper loss is happening because of this circulating current only.
Sir, this phasor means we are not taking angle.
Which phasor means? Oh, here.
Like even phasor minus E2 phasor.
Yeah, here no need to take phasor. Why? Because 445 angle 0 minus 455 angle 0. So both have the same angles. So both are with same reference. So it will not make any difference. Had it been different angles for E1 and E2, you could have taken the angle.
Sir, what is showing this phasor? I did not get.
Which phasor? This one, E1 minus E2?
Sir,
This one?
E1 minus or whatever quantity, like at the phasor, what that's showing?
First, please let me know. Are you talking about this expression? This one?
No, sir. Any of these, because sir, I want to know what is the meaning of this phasor. Phasor.
Okay, so see, if you will ignore the phasors, sorry, if you ignore the phasors from the expressions, let us suppose this expression I1 and I2, okay, these phasors, if you will ignore, then how will you compute exact values? See, E2 will have certain angle, Z1 will have certain different angle. And if you just straight away multiply and you ignore the angle, you will end up with different angles. So in AC or in transformer is a AC machine, and in AC machine, you are ignoring the phasors. It means it doesn't make sense because phasor is there to scatter the real power as well as reactive power. So you will not get any idea of real as well as reactive power along with the discrepancy in your values. Isn't it right?
Yes, sir. It means phasor means we have to consider both angle and magnitude.
Angles and magnitude, yes.
Okay, sir.
In this expression calculation, you must consider angles and magnitudes for all.
Okay, sir.
Okay. So that was this problem. Any final doubts on this problem? Okay, so since this problem was very exhaustive, I will try to take one very small problem, which will be very interesting for you. Okay, so just yeah. Are you able to see this problem clearly?
Yes, sir.
Okay, please read the problem, and if you know the concept, you will just tell me answer without pen and paper. Or you can use pen and paper if you wish.
Sir, 500 kV.
500 kVA. Okay, we will see. So which expression we can apply here? H2
Sir, both have
with
same kV rating.
kVA. Yeah. So we will see if both have same kVA rating. Okay, and the load is also 1000 kVA. What will happen if you go with the conventional expression? Okay. So just please bear with me for certain steps, and we will clarify this. Okay. SL into Z1 divided by Z1 plus Z2. So SL is 1000 angle minus 36.86, okay, into Z1. Huh. Now percentage impedances. Okay, so both are 500 kVA, so we don't need to change per unit values. If kVA rating of other transformers had been different, then you would require to change the per unit impedances. But since both are at the same kVA rating, you can just go ahead with the whatever is given. So here Z1 is 1 plus J6 divided by Z1 plus Z2. So 1 plus 0.8 plus J 6 plus 4.8. Okay. So it will end up with 1000 angle minus 36.86. Please calculate it. Plus J6.
Sir, 551, 55.5.
555.5 with angle.
Same, minus 36.86.
Is it?
Yes, sir.
Okay. So okay, this magnitude seems to be correct. I am skeptical about this angle, but anyway. So without pen and paper, you would have done a miserable mistake, right? So it's very important that you go ahead with the given expression, the conventional formula, to just avoid the mistake. Okay. Why is it happening? Because you have a certain power factor, and that power factor plays a very important role. How much power will be supplied from which transformer in what ratio, right? So do not get influenced just by seeing this 1000 kVA and 500 kVA are operated in parallel. Got it, Deepak?
Yes, sir.
Great. Neither you are getting this value.
Yes, sir.
Angle is also correct.
Yes, sir. Exactly the same.
Great, great. So this was very quick question. Another very small question is here. Okay. So please calculate it for me. I am taking 1 minute break. Okay. So please bear with that. Yeah. I'm back. So did you get the answer for this part?
0.025 per unit.
0.025 per unit. Okay.
Sir, I have 0.1 per unit.
0.1 per unit. So we have two answers. Any other answer? Okay, no one is. So, see, I told you when load is shared in proportion to their kVA ratings. It is written here very clearly that share load in proportion to their kVA ratings. In that case, Z1 per unit becomes equal to Z2 per unit. One condition I also mentioned in their on base. Okay. So what you did here, who calculated 0.025 per unit, you referred and you know transformed it to the same per unit, but it is mentioned that in their own base. Okay. So whatever 0.05 per unit was for first transformer, that will be again equal to 0.05 per unit. Okay. With 250 kVA. So its answer would be 0.05 per unit. Did you get it? Where did you commit mistake? This statement you should not undermine. This statement is very important. And Neeraj, how did you get 0.1 per unit?
So the ratio between the power that load was according to their KVA. So the ratio was 2:1. I equated it to the ratio of the equivalent impedances.
Like S1 by S2 is equal to Z2 by Z1 you did?
Yes, sir.
Okay. So let me compute. S1 is 500, S2 is
But sir,
250.
here it is inversely proportional.
It is inversely. I am doing inversely only.
We should do directly proportional.
Yeah, means I am going according to the Neeraj's method. I know
Yes,
it
sir.
is directly proportional, but what Neeraj did, I am just verifying it. Is it coming same or not? So Z2 is, we have to compute, Z1 is 0.05. So again, from this expression also, it will come out to be 0.025. Okay, so anyway, you have to avoid such mistakes, okay? And this is very important when load is proportional to their KVA ratings. We have to just equate, okay, just equate per unit values if they are given. If actual values had been given, you could have computed per unit values in their own basis, okay, and then you equate. Okay, is it clear?
Okay, sir.
Okay. Any other question? Okay. So in here, this part 3, this problem, here we have circulating current. This problem I am not going to solve. Why? Because it will again take very high time. So it is based on the circulating current wala that equivalent circuit, because no load voltages are different, right? So again, they are sharing certain load with certain power factor. Power factor is again pointed, which is pretty common here. So first you need to calculate the circulating current, which is pretty easy. In part B, the complexity will arrive that what is the percentage of load shared by the both transformers, transformer 1 and transformer 2. So it is similar to the problem what we solved in part B of the first problem, right? Here, when no load voltages are different, how much load will be shared from both of them. So if you will able to solve, and in the next session I would like to have an answer for this, okay, and I will have answer at my side also, and we will verify. And if you are able to solve with correct answer, it means you have got the entire point of circulating current when both the transformers are connected in parallel, right? So you try it on your own. It will
Okay,
be
sir.
interesting to solve it, okay? And the other part is, this problem is based on per unit values. So here we will solve it very quickly, because we have to compute no load circulating current, ohmic losses, and no load LV side terminal voltages. Okay, so we will solve it very quickly here. So how to go ahead? Circulating current is very easy, right? E1 minus E2 divided by Z1 plus Z2. Okay, so we have to consider here, because 240 volt is in the transformer 1 and 230 volt is the rating of the transformer 2. Okay, so now is Z1 is 1 plus J 4.25 percentage. It is given in per unit, and to calculate circulating current we need actual values. Okay, so first thing we need to do, we have to compute actual value. Z1 is equal to 0.01 plus 0.0425 divided by
So multiplied.
yeah, thanks, multiplied with base value. into Z base. Okay, so Z base will be equal to kVA square by MVA. So 240 square storage base by 300 kVA, and it will come out to be 240 square divided by 300 into 10 to the power 3. It will come out to be 0.192. 0.192. Okay, so now Z1 actual will become 0.00192 plus J 0.00816. Okay, similarly Z2 actual will be equal to 0.0125 plus J 0.055 into Z base 2. Okay, Z base 2 here is kVA square 230 square divided by 200 kVA. It will come out to be 0.2645. And if you multiply with base, you will get into 0.0125. You will get 0.003 plus J 0.014. Okay, so we have computed actual values of Z1 and Z2. Now we are ready to compute the circulating current here. I circulating will be equal to E1 minus E2, 240 minus 230 divided by Z1 plus Z2. So 0.00192 plus J 0.00816 plus 0.003 plus 0.01.
Sir, here we cannot add in per unit impedance.
These are actual values, right?
Yes, sir.
Because in per unit you can do, but what will happen that per unit values are given in their own basis. So you have to convert with common basis, and then you have to write, right? So 240 volt, if you take as a 1 per unit, then 230 volt will be 230 by 240 into 1. So accordingly you will have a high confusion, and I think there is high probability that you will end up with doing certain mistakes. So it is better that while you are calculating the circulating current, you just go ahead with the actual values, right?
And sir, base value we can calculate from these rated voltage and kVA rating.
Yeah, because if you straight away use these per unit values, they are given with their own basis. This 1 plus 4.25%, they are given with 300 kVA and 240 volt. So you have to make a common ground for both the impedances. Okay, so
But sir,
if you
here they did give in percentage. We have to divide by 100.
100, yeah, first thing that you have to divide it by 100. That
We
I
got
by
per unit.
default, by default I moved ahead with division by 100.
Yes, sir.
So if you calculate these values, okay, so you will get approximately 429.2 with certain angle that will be minus 77 degree. So this much circulating current is there, okay. And if this much high circulating current is there, in part B, it is asked that estimate the ohmic loss caused by the no load circulating current. So you have to just multiply 429.2 square into 0.00192 plus 0.003. So whatever you will get, that will be
Ohmic losses.
962.5 watts. So 962.5 watt is the losses here, okay. And the last part is the estimate the no load LV side terminal voltage. Okay, so what will be the expression for computation of no load LV side terminal voltage? You have to just apply the KVL, right? You want this voltage at the terminal. So let me bring back the circuit. So you see this circuit, right? So you need this voltage at no load. It means this is disconnected. So VT will be equal to E1 minus I1 into Z1, right? Or E2 minus I2 into Z2. So anyway, you can end up with the terminal voltage.
So here we don't need to check from both sides. Anyone from
Anyone will give you the same answer by the virtue of KVL. It will not violate. Right? So
Okay,
from
sir.
any side, you can do E2 plus I2 Z2 and E1 plus I1 Z1.
Okay, sir.
So no load voltage VT, we are computing VT will be equal to E1 minus I1 Deepak, certain noise is coming from your side. So E1 is equal to 240 with minus I1. We have computed I circulating current, right? So 429.2 and E1 angle 0, 429.2, and we had certain angles, right? Minus 77 degree into Z1. So Z1 is 0.00920, 0.00192 plus J 0.00816. So if you will compute this expression, you will end up with certain value that will be 236.4 volt. Okay, it will have certain angle that you can compute. Any doubt? So at no load, terminal voltage will be this much. Okay. So this is a very standard. These three problems what we discussed today. It has almost higher than 95% probability that you will get in exam any one of out of three. So please be well versed with these problems. Okay, these are very important problems, and at the same time, it is a bit confusing because different value of base values and per unit values. But this is all. Any final doubt regarding any problem, any part?
Sir, in practical, we don't want circulating current.
Right, we don't want.
Like we are seeing so many transformer in around us. They are all connected in parallel, but they cannot carry any circulating current.
Practically, it is impossible to balance all the transformers. So there are certain circulating currents which are flowing through them, but that is the way we have to live with it. But most of the times, engineers try to balance them, but it is very difficult to match the accuracy. So, but that circulating currents are generally very less. So we do not worry about that in practical, right?
Okay, sir.
Yeah. Any other doubt before we wind up the session?
No, sir.
Okay, great.
Sir, I
So,
have a last doubt apart from
yeah,
this study.
yeah, go ahead.
Sir, you did got these all the concept during the your BTech journey or MTech?
These concepts I learned during my undergrad,
Sir, BTech.
BTech, yeah.
Sir, because I have studied electrical machine one and teachers don't tell these all concept for me.
Yeah, it happened for me, unfortunately, as well. But you have different channels where you can get all these knowledges. So it happens that somewhere you don't get even, in certain very good colleges also, it is difficult to handle all those concepts in much detail. So it's our responsibility to get well versed with all those concepts, and because at the end of the day, you have to solve the problems which will come in the exam, right? So it's our responsibility. So consider it as your responsibility to learn all the concepts based on whatever important subjects, whatever area you are going to pursue. So it happens frequently, more often, that you don't get taught very good in your institute, but this is the way, right? Because at the end of your engineering, you cannot blame that it was not taught in my institute, or even if you blame
Yes,
that,
sir.
no one will be there to listen.
Yes,
So
sir.
it's better to be prepared than blaming others,
Yes, sir.
right? So if any doubt there, you can always contact me if anything you need. But I think NPTEL
Yes,
is
yes,
fulfilling
sir.
most of the things. Yeah.
Yes,
Okay,
sir.
sir.
Bye,
Thank you,
sir.
sir.
Good night.
Thank you very much. Good night.